All right, chapter 36, geometric optics, problem number 1. A clown 2 meters tall looks at himself in a full-length mirror, floor to ceiling. Where in the mirror must he look to see his feet? Well, let's take a look at this. We've got a full-length mirror, and a clown. I guess we need to put some big shoes on him. And wants to look at his feet. So the feet are going to have an image. This is 6 feet. No, 2 meters tall. I didn't say 6 feet. It's 2 meters. We want to see the feet. The feet are going to project a light as real ray light, and for that to reach the clown's eyes, we'll have to go basically about halfway up on the mirror, because the angle of incidence will equal the angle of reflection, and so we have to travel the same distance angularly to the mirror and then back to the eyes. So that'll have to be about 1 meter, and that'll have to be about 1 meter to do that. So the clown will have to look about midway up on the mirror, which would be about 1 meter from the floor. Problem number 2. A concave mirror has a focal length of 20 centimeters. What is the position in centimeters of the resulting image if the image is inverted and 4 times smaller than the object? Problem number 2. We're told that the image is inverted and 4 times smaller than the object, so we can say that the magnification should be negative because the image is inverted, and the magnification should be 1/4 because the image is 4 times smaller. So in terms of magnification, that's equal to the negative image distance q over object's distance p, and we're going to say that that's a negative 1/4 inverted and 1/4 for the image size. So solving this for p, multiplying both sides by a -1 and bringing p over here and the 4 up here, we have 4q equals p, or p is equal to 4q. So far so good. Now we have a concave mirror, so we're going to apply the mirror equation, which means 1 over the object distance plus 1 over the image distance equals 1 over the focal length. And since p is equal to 4q, we can say that 1 over 4q plus 1 over q is 1 over the focal length. In this case, the focal length is given as 20 centimeters. So we have 1 over 4q plus 1 over q equals 1 over 20. Let's just keep everything in centimeters, so our answer will be in centimeters. And multiplying this by 4 over 4 and get a common denominator, we'll have 1 plus 4 over 4q equals 1 over 20, or we'll have 5 times 20 equals 4q, or q will equal 100 divided by 4, or 25 centimeters. So our answer is 25 centimeters. Now, this is a concave mirror. So imagine what it might look like here. Generally, the radius would be twice the focal length. Let's say that's the focal point right there. And so if the position, see, the image is going to be outside the focal point inverted, something like this, and p is equal to 4q, and if that's about 20, then p would be way out here somewhere, maybe. There's our object. Here's our image. And one way it might work is any ray that went through the focal point will come out parallel. And draw that very straight. Come out parallel, so this point of this object will hit this point here. Anything that hits in the center of the mirror will reflect like a flat mirror, come out straight like that. So actually those two rays would define that point for the image. And last thing I could do is bring in a ray that came in parallel. Anything coming in parallel will reflect back through the focal point like that. So I could have chosen any two of those three rays, and that would help me set up where the image was. The image ends up being just beyond the focal point, but inverted and 1/4 as large as the object. Problem number 3. A convex mirror has a focal length of -20 centimeters. What is the position of the resulting image in centimeters if the image is upright and 4 times smaller than the object? Okay? Take a look at this. We're told that the image is upright and 4 times smaller than the object. Again, we would say that the magnification should equal a negative image distance over object distance. But if it's upright, then the magnification will be positive. And if the image is 1/4 as large as the object, then our magnification will be 1/4. Based on this, again, let's solve for P. And we have bring 4 over here and P up there. -4Q equals P, or P equals -4Q. And we'll apply the mirror equation again. So we have 1 over object distance plus 1 over image distance equals 1 over focal length. And so we'll have 1 over -4Q plus 1 over Q equals 1 over focal length. In this case, focal length was given as a -20. So let's put that in there. Find a common denominator here. We'll multiply this by -4 on either end. So we'll have 1 plus -4 over -4Q equals a -1 over 20. This would be a -3 times a -20 equals a -4Q, or Q equals 60 divided by 4, or 15 centimeters. So our answer, did I do that right?
Should be negative?
Should be negative. Good. Right.
Right, because that 3 times 20 would be positive divided into, yeah.
Should be negative.
Gotcha.
Yeah, with the negative written in that step. -15 centimeters. Okay. We have it's a convex mirror. Kind of look like this. And let's see, the focal length is a -20, so somewhere in here is a focal point. And let's say if we had an object, let's see, Q is a -15, so that means P would be about 60. This way. So let's say our object was somewhere over here. And so if I had a ray coming in to the center of this mirror, it would pretty much reflect like a flat mirror, at least at the center. And it would appear to come from this direction like this. in that sense. Now, if I had a ray coming straight in, it actually would reflect off, and the direction it would reflect off something like this. So it actually would appear to come in from the direction of the focal point, and that actually is good enough. That's all we really need. So right there is our image, and that would be about 15 centimeters away from the front of the mirror. It's a virtual image because it's not actually comprised of the real light rays. The real light rays are on this side of the mirror, and magnification is positive, so it's upright. Negative means it's behind, it's not actually comprised of real rays. It's actually on the side where there are no real rays, so that's why it's a negative distance for the image distance. Well, number 4, a concave mirror has a focal length of 20 centimeters. What is the position in centimeters of the object if the image is upright and is 2 times larger than the object? Okay, this is on number 4. Magnification, again, will be negative image distance over the object distance. And we're told that the image is upright, so that's going to be a positive magnification. And the image is 2 times larger than the object, so the magnification is 2. So this is 2. So again, let's solve this for, see, we want to find what's the position of the object, so we want to find P. So let's solve this for Q in terms of P. So Q will equal a negative 2P. Put that into the mirror equation. 1 over P plus 1 over Q equals 1 over the focal length. And so we have 1 over P plus 1 over a negative 2P plus 1 over the focal length. We're told that the focal length is 20 centimeters. So this will be negative 2 plus 1 over negative 2P plus 1 over 20. So that's going to be negative 1 times 20. So negative 20 will equal a negative 2P, or P will equal 10 centimeters, positive 10 centimeters. So, this is a concave mirror. Let's take a look at this. Something like this. And say this is the focal point. And we're actually going to have a object that is inside the focal point. So maybe I can move this back a little bit. So that might be, maybe this might be our object right here. And if I were to think about how this might work, if I had a ray that came in parallel, then I would expect it to reflect through the focal point, like that. And if I had a ray that came in to the center of this mirror, I would expect the angle of incidence to equal the angle of reflection. So it would come out straight out like this. we can kind of see that these rays are diverging on this side of the mirror, so we're expecting that they're going to converge on the other side. And if I were to follow this back, where they do converge, this is a little bit exaggerated, would be an image. So this is the object, and here's the image. Now we can see that the image is about just about twice the size of the object, roughly, and it is upright. It's not inverted, so it's positive. And it's virtual. And so our image distance is going to be negative because it's now on the side of the real rays. And our object distance is positive, and it seems to work. Problem number 5. The concave mirror has a focal length of 20 centimeters. What is the magnification if the object's distance is 100 centimeters? All right, so we're given in this problem that the focal length is 20 centimeters and the object's distance is 100 centimeters. And we want to find the image distance, so we're going to apply the mirror equation. So 1 over P plus 1 over Q plus 1 over F. And so we have 1 over Q is equal to 1 over F minus 1 over P. That's 1 over 20 minus 1 over 100. So that's going to be 5 minus 1 over 100. 4 100ths, or 1 over 25. So Q is going to equal 25 centimeters. Positive quantity. We want to find the magnification of this object. By definition, the magnification is a negative Q over P. So this would be a negative 25 over 100, which would be a negative 1/4. So the image will be inverted and 1/4 the size of the object. Problem number 6. A convex mirror has a focal length of minus 20 centimeters. What is the object distance if the image distance is negative 10 centimeters? Okay, so the focal length is a negative 20 centimeters. Image distance is a negative 10 centimeters. And again, starting from the mirror equation, solve this for the object distance. That's going to be 1 over negative 20 minus 1 over negative 10. Multiply top and bottom of this one by 2. So we'll have 1 minus 2 over negative 20, which will be negative 1 over negative 20, which will give us 1/20th. And hence, if I can fit it down here, P would be equal to 20 centimeters. So the object distance will be 20 centimeters. Problem number 7. A concave mirror has a focal length of 20 centimeters. What is the magnification if the object and image distances are 10 and minus 20 centimeters respectively? All right, number 7. What was given? We have a concave mirror, focal length of 20 centimeters. And the image distance is 10 centimeters. And the object distance is minus 20. The object and image distances, I got those reversed. All right. Object is 20, image is minus 20. the way it's phrased. And we want to find the magnification. By definition, the magnification is a negative image distance or object distance. So this would be a negative 20 over 10, which would be 2. And that's it. Answer B. The focal length would be extraneous information for this problem. Problem number 8. A concave mirror has a radius of curvature of 1 meter. An object is placed 2 meters in front of the mirror. Determine the location of the image in centimeters. All right, problem number 8. We have a concave mirror, radius of curvature of 1 meter. Now the focal length is equal to the radius of curvature divided by 2. Or in other words, the radius of curvature will equal twice the focal length. So let's go ahead and just say that that would be 1/2 of a meter. And so we have 1 over object distance plus 1 over image distance equals 1 over focal length. And so we have, let's see, object is placed 2 meters in front. So we have 1 over 2 plus 1 over q equals 1 over 1/2, which would be 2. So 1 over q is going to be 2 minus 1 over 2. And so it's 3/2, or q equals 2/3, 0.67 meters, positive. And so that'll be the location of the image, 0.67 meters. Positive, which means it's on the, well, it's a mirror, so it's on the same side as the rays coming in. Problem number 9. An object 4 centimeters high is placed 15 centimeters in front of a convex mirror with a focal length of minus 10 centimeters. What is the image position in centimeters? Let's write down what we know on this one. An object 4 centimeters high. Hang on to that. Well, let's just say that 4 centimeters high is the height. Let's place 15 centimeters in front of a convex mirror. So our object distance is 15 centimeters. With a focal length of minus 10 centimeters. And we want to find the image position. So again, we use the mirror equation. 1 over object distance plus 1 over image distance equals 1 over focal length. Solve this for q. 1 over q equals 1 over f minus 1 over p. Must be 1 over negative 10 minus 1 over 15. Let's use a common denominator of 30. So this would be, multiply this by 3 over 3. So we'll have a negative 3 over 30 minus 2 over 2, which will give us 2 over 30. Negative 3 minus 2 will give us a negative 5 over 30. So Q, so it would be negative 1/6. So Q equal a negative 6 centimeters. And the negative in this case, since it is a convex mirror, which means that after reflection, the rays are going to diverge. So the image is actually going to be on the inside of the mirror, not where the real rays are. It's going to be on the opposite side of the mirror, which means that's why the image distance will be negative. Problem number 10. An object 15 centimeters high is placed 15 centimeters in front of a convex mirror with a focal length of minus 10. What is the image height in centimeters? All right, and this problem number 10 is actually the same setup as the previous problem. In the previous problem, we place an object 15 centimeters in front of a convex mirror with the same focal length. And we found in that situation that our image distance was -6 centimeters. That was our result from problem number 9. So, in this one, we would say the magnification is a -q over p. And so that would be equal to a -6 over 15, which would be 6/15 or 2/5. And so our magnification is a positive 2/5, which should be equal to the image height over the object height. In other words, what our image looks like compared to the object. So we could say then that our image height will equal 2/5 our object height, and our object height was given as 15 centimeters. So that's going to be 15 divided by 5, which would be 3, so that would be 6 centimeters. So our image height will be equal to 6 centimeters. Number 11, an object is placed 10 centimeters in front of a concave mirror with a 20 centimeter focal length. Determine the image location in centimeters. Number 11.
Number 11.
Object distance is 10 centimeters. Concave mirror with a 20 centimeter focal length. And we're going to use the mirror equation. 1 over object distance plus 1 over image distance equals 1 over focal length. We want to find the image distance. So we have 1 over q is 1 over focal length minus 1 over image distance. So that's 1 over 20 minus 1 over 10. So that would be 1/20th minus 2/20ths, which will give us a -1/20th. So fit it in there. So q will equal a -20 centimeters. And so that is our image location. It is a concave mirror. So again, the image might come in and diverge, something like this. And so the image will be found behind the mirror, and that's why it's a negative number. Problem number 12. An object is placed 15 centimeters in front of a concave mirror with a focal length of 30 centimeters. What is the magnification? All right, here's number 12. Object is placed 15 centimeters in front of a concave mirror, so our object distance is 15 centimeters. Focal length is given as 30 centimeters. We want to find the magnification. Let's find the image distance first. So 1 over p plus 1 over q plus 1 over f. So 1 over q is going to equal 1 over f, 1 over 30 minus 1 over 15. Think of this as 2/30ths. So this would be a negative 1 over 30. So q will equal a negative 30 centimeters. And so magnification is a negative q over p. So that's a negative 30 over p, which is 15. Gives us 30 over 15 over 2. So the magnification will be 2. Image will be upright and twice the size of the object. 13. A dentist uses a concave mirror, focal length of 2 centimeters, to examine some teeth. If the distance from the object to the mirror is 1 centimeter, what's the magnification of the tooth? All right. Problem 13. So again, we have the mirror equation. And in this case, we're told that the focal length is 2 centimeters. And distance from the object to the mirror is 1 centimeter. So that would be our object distance. We'll solve this for Q. So we have 1 over Q will equal 1 over F minus 1 over P, which would be 1 over 2 minus 1 over 1, which would be a negative 1/2. So Q will equal a negative 2 centimeters. And hence our magnification, which is a negative Q over P, will be a negative negative 2 over 1 or 2. So the dentist will see in an image that is upright, so that's good, and it'll be twice the size as your tooth, so maybe they can see if there's a cavity there or not. 14. The actual depth of a shallow pool, 1 meter deep, is not the same as the apparent depth seen when you look straight down at the pool from above. How deep will it appear in centimeters? Let's take a look at this. Let's say you're to look down at something, actual depth of a shallow pool, 1 meter deep. So let's say here's our object, 1 meter deep, fish here. So we'd actually say that here's where our rays are originating, within the water itself. So here's our index of refraction for where the object is, water, and here's our index of refraction for where the image is going to be. So the rays are going to go up like this. And we find that the image distance will equal a negative of the second index over the first index times the object distance. In this case, object distance will be 1 meter, and the first index is where those rays originate, so that's going to be 1.33. The second is going to be where it goes after the interface, which will be 1. So this would be negative 1 over 1.33 times 1 equals a negative 0.75 meters, which means that the image is going to appear on the same side as where the ray originated. In other words, the rays are coming up here, but the image is going to appear somewhere around here. So as you're looking down, it's going to appear like the fish is only 3/4 of a meter below the surface of the water when it's actually 1 meter below the surface of the water. And so if you're trying to survive by catching that fish with a net, you might be swinging a little bit too shallow in order to actually catch the fish because you think he's closer than he actually is. Problem number 15. Bottles of perfume sometimes have thick glass, index of refraction 1.5, walls which give the impression that the volume is larger than it is. Assume a cylindrical bottle has an inner radius of 1 centimeter and an outer radius of 2 centimeters. How thick in centimeters would the wall appear if you could see a mark on the inside surface? Well, let's take a look at this bottle of perfume. Let's take a top look at this bottle. So we're told it's cylindrical and it's got an inner and outer radius. So let's say this outer radius here is 2 centimeters and this inner radius is 1 centimeter. So here's the glass itself, index of 1.5. And we're told that if you want to look at a mark on the inside surface, where would it actually appear to be? And so we want to find the image distance. Well, let's say there's some mark here on the inside surface here. And so what we're looking at is the object is here. We have an inner radius. We have 2, if you would, concave surfaces for this, what would be a lens. So let's find the focal length from the lens equation. So we got 1 over the focal length will equal the index of refraction minus 1, 1 over the radius of the first surface minus 1 over the radius of the second surface. And so if we put this in, this being the object, and we're headed this way to look at it somewhere over here, then we would write 1 over the focal length equals index 1.5 minus 1. The first radius is 1 centimeter. Second radius is 2 centimeters. That's going to be 1 minus 1/2. Sorry, this would be, both of these would be negative because they're both concaved in. And so the radius of curvature is actually on the side, not on the image side, which would make it a positive radius. It's on the object side. So if it's not on the actual side of the outgoing rays, then we think of the radius of curvature as being a negative value. So both of those are negative. So if I put that in, I'll get 0.5. And this would be negative 1 plus 1/2, which would be a negative 1/2. So this would be a negative 0.25. So the focal length will be 1 over negative 0.25, or negative 4 centimeters. That's kind of nice to know. So now we want to find the image distance, and we're going to apply the lens equation. 1 over object plus 1 over image distance equals 1 over focal length. Solve this for 1 over Q. This would be 1 over a negative 4 minus 1 over, now our object, as far as this lens is concerned, is going to be 1 centimeter away from the outer surface. So put 1 in there. And if I figure this out, then this will be, multiply top and bottom of this by 4. So this would be a negative 1 minus 4 over 4. This would be a negative 5/4. So Q will equal a negative 4/5, or negative 0.8 meters. The negative sign means that the image is not going to be on the side of the outgoing rays. Here the rays are coming here and they're headed this way. The image is actually going to be located on this side of it at a negative 0.8 meters. So, 0.8 centimeters. We're staying in centimeters. So it's going to be located right here. If this is 1 centimeter thickness, it's going to be located right about on this radius right here, 0.8 centimeters in. So it will appear to an outside observer that this inner radius, or this inner sanctum where the perfume is actually wider than it actually is, because this inner surface appears to be closer to the outer surface than it actually is, making it look like it's bigger inside, but it's actually not. Problem number 16. Bottles of perfume sometimes have thick glass, index of refraction 1.5 walls, which give the impression the volume is larger than it really is. Assume a cylindrical bottle, inner radius of 1 centimeter, outer radius of 2 centimeters. What percentage of the apparent volume is the real volume? Well, this is the same problem that we had in problem number 15, only now it's asking what percentage of the apparent volume is the real volume. So, it appears to look bigger than it is, and so what percentage of that is the real volume? So what we could say, let's just kind of continue this, is if we were to take the volume of the real volume to the apparent volume and compare that ratio. Now we're looking at a cylinder, so we're looking at the the cross-sectional area of a circle multiplied by the length of the cylinder. If it has some kind of length, then the volume would be this cross-section times the length. And so we're going to say that the real volume will be the length times the cross-sectional area, which will be pi times the real radius squared. You know, the cross-sectional area times length. And we could say that the apparent volume will be the length of the cylinder times the cross-sectional area, which would be the radius of the apparent squared. Be that ratio right there. These lengths will cancel out. The pi will cancel out. And so what we really want is the radius of the real cylinder squared to the radius of the apparent cylinder squared. Now the real cylinder, inner cylinder, is actually 1 centimeter radius. The apparent radius of the inner one is going to be 1.2 centimeters because we thought from the apparent depth that the inner radius was only 0.8 centimeters in. So that means we think by the appearance that the apparent inner radius is 1.2 centimeters. In other words, it's 2 centimeters minus 0.8. So as we put that in here, this would be 1 squared over 1.2 centimeters squared. And that gives me a number of 0.694 or 69.4%. What it means is we're thinking we're getting a certain amount of perfume, but we're actually getting only 69.4% of that amount. We're actually, through the appearance and through the deception of the glass, we're actually losing 30% of that perfume. Problem number 17. A plain convex lens is made of glass, index of refraction 1.5, with one flat surface and the other having a radius of 20 centimeters. What is the focal length in centimeters of the lens? Okay, let's take a look at this. We have ourselves a lens, which we're going to comprise of 2 surfaces. It might look something like this. The first surface has a radius of curvature of 20 centimeters. And the second surface has a radius of curvature of infinity because it's a flat surface. I mean, so the radius would be infinitely large. And so if we were to look at this index of refraction 1.5, then we have from our lens maker equation 1 over the focal length equals n minus 1 times 1 over the first radius minus 1 over the second radius. As we're looking at this lens in this direction. So our first radius will be 20, second radius infinity. So this will be 1.5 minus 1 over 1 over 20 minus 1 over infinity, making that 0. This would be 0.5 divided by 20, and that gives me, well, we can flip them. So we can say the focal length would be 20 divided by 0.5. So that would be 20 divided by 1/2, or 40 centimeters. So our focal length for this lens is a positive 40 centimeters. 18. An object 20 centimeters high is placed 50 centimeters in front of a lens whose focal length is 5 centimeters. Where will the image be located in centimeters? All right, here's 18. We have an object 20 centimeters high. So we'll say that's the object height. 50 centimeters in front of a lens. So the image, the object height. Image would be 50 centimeters. The object distance and the focal length is 5 centimeters. So we have 1 over the object distance plus 1 over the image distance equals 1 over the focal length. Solve this for the image distance. 1 over Q equals 1 over F minus 1 over P, 1 over 5 minus 1 over 50. So this would be 10 50ths minus 1 50th, or 9 50ths. So Q will equal 59ths, which would be 5.55 centimeters. So our image distance will be 5.55 centimeters. That is a positive value, so that means it's on the outgoing ray side of the lens, on the same side as the outgoing rays. Problem number 19, an object 20 centimeters high is placed 2 meters in front of a lens whose focal length is 5 centimeters. What is the size of the image in millimeters? Well, not a whole lot different from some of the other problems, except we're getting a mixture of sizes here. The object is 20 centimeters high, so let's just write that down. Let's stay in the centimeter realm. That seems to be working. And it's placed 2 meters in front of a lens, so our object distance is 2 meters, which I'll write as 200 centimeters. And the focal length is 5 centimeters, so that's... And we want to find the size of the image. All right. So let's find the image distance first. So we have 1 over object distance plus 1 over image distance equals 1 over focal length. 1 over image distance will equal 1 over focal length minus 1 over object distance. 1 over 5 minus 1 over 200. And so that's going to be 40 200ths minus 1 200, or 39 200ths. So Q will equal 200 divided by 39, which is 200 divided by 39. That's the way I left it. So let's leave it like that for the moment. We know the magnification is equal to negative Q over P, but it's also equal to the image height over the object height. So that's going to equal a negative 200 over 39 over P, which is 200. Oh, P, which is 200. And so this will equal negative 1 over 39. So we have image height or object height equals a negative 1 over 39. So image will equal a negative 1 over 39 times 20, which would equal a negative 0.513 centimeters. That would be the image height. We were told to put the size of the image in millimeters. So this would be approximately a negative 5 millimeters, or 5.13 millimeters. So the size would be the magnitude of that, which would be 5 millimeters. Problem 20. An object 50 centimeters high is placed 1 meter in front of a converging lens whose focal length is 1.5 meters. Determine the image height in centimeters. Well, let's see, object 50 centimeters high, so let's write that. Object height. Place 1 meter in front of a converging lens, so I'm going to go ahead and say that my object distance is 100 centimeters. Of course, they did put the focal length in meters, so I probably could have left it like that. Oh well. Focal length is 150 centimeters. Let's find the image distance, 1 over P plus 1 over Q plus 1 over F. So 1 over Q is going to equal 1 over 150 minus 1 over 100. Yeah, I should have left it that way. Let's use 300. So this would be 2 300ths minus 3 300ths equals a negative 1 over 300. So Q will equal a negative 300 centimeters. And since magnification equals a negative Q over P, that's equal to image height over object height. And we want the image height, so the image height will equal a negative Q over P times the object height. So that's going to equal a negative 300 over 100 times 50. Negatives cancel out, so that's going to be 3 times 50 or 150 centimeters. So the image height will be 150 centimeters, 3 times the object height.